I have a great problem in giving this talk because I don't quite know what the subject is about. The reason being that, being older than a lot of you now, I suppose, I was there when the term magnetosphere was invented. And the magnetosphere at that time, and I hope now, means the region between about 120 kilometers and everywhere else in the Earth's magnetic field. So it's a little difficult to talk about magnetosphere-ionosphere coupling, since the ionosphere is in fact part of the magnetosphere. What I did just to make this point was to dig out a few ancient papers, just at random, which was sufficiently ancient that the author felt that he had to define or remind his reader what the magnetosphere was in the first place. I don't know if you can all read that, but the first I just clipped out of a review paper by Colin Hines, and he just points out that the magnetosphere is defined by its dynamical behavior. It's that part of the Earth's environment in which the motion of ionization is dominated by the magnetic field. That's the most important thing of all. You can see then why it's the region from the ionosphere upwards, of course, because the motion of plasma in the ionosphere is dominated by the Earth's magnetic field, at least above altitudes where the gyro frequency is comparable to the collision frequency. Now, at times, one likes to, in fact, push this even down further and take it down to the place where the electron gyro frequency is comparable to the electron collision frequency, which brings the thing down to maybe 90 kilometers. Essentially, the definition that I gave you amounts to the following, that the magnetosphere is the place where E plus V cross B is a good approximation for Ohm's law, at least in general. That is, the mean motion of plasma, at least of the lower energy plasma, is essentially E over B. Right, well, I thought then I ought to say what magnetosphere-ionospheric coupling might be, if there was any necessity for saying so. If we divide the magnetosphere into the ionosphere and the rest of the magnetosphere, then we more or less have it right. And then the coupling can be thought of in a simple-minded way, at least very simply. The coupling can consist of exchanging mass, exchanging momentum, exchanging energy between the various regions. And in the process of doing this, you might think about the exchange of stresses hydromagnetically, or if you want to think of it another way, the exchange of current and electric field. Now, first of all, in mass exchange, if we consider the various possibilities that we have from the ionosphere upwards, so the first line there reads up, the exchange of mass, which is important, is essentially the polar wind, if you like, or the processes which cause the ionosphere to flow upwards and in some parts escape from the Earth altogether, or in other parts of the magnetosphere replenish or build up the plasmasphere. Just from looking at the way the plasmasphere sits in the middle of the magnetosphere, it seems pretty clear that beyond the average position of the plasmasphere, which is latitudes of 60 to 65 degrees, essentially anything that flows upwards is lost by one way or another. It may not flow out along open field lines immediately, but it gets lost pretty soon afterwards. There's good evidence now from the measurements of the Lockheed group that there are energetic, singly ionized oxygen and helium ions in the magnetosphere, ions with energies of a few kilovolts. And it seems quite impossible to get these from any other source but the ionosphere. For instance, solar wind oxygen ions have all the wrong characteristics. To begin with, they're charged maybe 6 or 7 times. It's very difficult to get them all neatly down to be charged only once without doing worse damage. And furthermore, the energies are all wrong. The energies of a few kilovolts are just wrong for solar wind oxygen ions, which begin with energies of several kilovolts when they're outside the magnetosphere. If you bring them into the position where these ions are observed, they must inevitably be accelerated no matter what happens to them. So they ought to have energies of some tens of kilovolts at the positions where they're observed. And that's not the case. So I think it's pretty clear that these are ionospheric ions which have been accelerated to modest but significant energies. About how do outer magnetospheric features relate to ionospheric features. It's a rather complicated one. In the outer magnetosphere, we have everything nicely controlled by the Earth's magnetic field, but unfortunately it's rather difficult to understand just what the shape of the Earth's magnetic field really is. I think Don Fairfield has wrestled with this problem more than anyone. But one always knows that if you're out in the magnetosphere looking at the results, observations of one particular satellite, one can never be very, very confident about where the field line at your satellite happens to hit the Earth, or even where the field line goes when it's in the opposite direction. There are endless arguments about how far field lines are extended into the tail and where field lines in the vicinity of the polar cusp go. Do they straggle back into the tail, or do they close on the Earth comparatively closely? Now, if one wants to think about other modes of transport or think about the actual mode of transport of momentum and so on between the outer magnetosphere and the ionosphere, the best way, as far as I can see, is to think of stresses. Now, I'm going to talk later in terms of currents and electric fields, but that is not a very convenient way to do it always. One can't understand the whole problem of coupling, I think, unless one thinks of forces or stresses in the first place, because the magnetosphere is a very complicated place, and it's almost a waste of time unless you think of the problem in some self-consistent way. By that I mean that the current, for example, in the magnetosphere is not just a current which God gives you. Somehow or other, the current has to fit itself in nicely with B, because there's a nice equation relating them, J equals quel B. And you can't just say that the field is there, let a current flow. It isn't like that. The way the magnetosphere is built is that all the currents close within the magnetosphere. It's not like a laboratory plasma where you might be able to close some currents in some external circuitry, and you have external pieces of concrete and pieces of steel and pieces of glass which take up stresses for you. In the magnetosphere, all the stresses exerted by the plasma and by the magnetic field must be in balance between each other. You can't have anything externally holding on to things for you. It's too easy to think that you've discovered something in both solar flares and in the magnetosphere by saying that, well, the current was interrupted. So that in itself is a big zero, because everyone knows that during a substorm the magnetic field changes. Everybody knows that J equals curl B, and so if the field changes, then you know the current changed. So it was interrupted, if you like. So you don't know anything more by saying that. What you have to really understand is why the current was interrupted. In other words, why the field was changed.